Thanks, and thanks for coming to my talk, everybody. I appreciate you being here today. I hope you're enjoying Hack in the Box as much as I am so far. So yesterday, I saw a really cool talk called ARMX. It was a new tool that was being introduced for looking for problems in the software parts of embedded systems, so the firmwares. It was a cool emulation framework for analyzing software. Today, we're going to talk about looking at the hardware parts of embedded systems with another new tool that I'm going to introduce to you today called Scapula. So before I get started, a little bit about myself. So again, my name is Wright, and I'm a software engineer most of the time. I'm a lot more of a builder than I am a breaker, actually, but today will be the exception to that. I work for a company called Assured Information Security, and as a disclosure, a part of the work that I'm showing today has been partially funded by the United States Department of Defense, so just a disclaimer on that. But my interests generally include low-level bits and bobs, things like hypervisors, embedded systems. I really like things that concern interactions between software and hardware. That's kind of what's up my alley. So I'm also a big outdoor enthusiast. I'm a really big rock climber, so if anybody has any rock climbing data for around the UAE, I'd love to hear about it after my talk. So I got to give you a few boring details about my day job before I talk about some cool tools that I've kind of introduced today. So I spend a whole lot of my time working on this open source project called the Bearflank Hypervisor SDK. So basically what it is, it's an open source toolkit for you all to write your own bare metal hypervisors in C++. If you're not familiar with what a hypervisor is, that's the technology that sort of fundamentally drives virtual machines. So if you ever use things like VirtualBox or VMware or heard of any bare metal hypervisors like Zen, things like that, that's what a hypervisor is. So Bearflank is a toolkit for letting you write your own bare metal hypervisors more easily. The really cool part about it, though, is that although it lets you write bare metal hypervisors, you can start these after an operating system is already running on your computer. So in other words, you can have, say, Windows running on a computer. You can start Bearflank after Windows is running, and it will lift Windows off the hardware into a virtual machine while it's running. And I will let you guys fill in the gaps about why that might be useful or interesting. But anyways, so a large portion of what I do in this Bearflank project really revolves around this. So does anybody recognize on the left-hand side of this slide that cover page? Nobody? Yes, I hear. So this, if you don't recognize it, this is the cover of the Intel Software Developers Manual. I kind of live and breathe by this manual. It's basically, it is the source of information about the Intel microarchitecture. Everything you'd want to know is in there. So a lot of my project really revolves around this idea of the developers go and read this manual. They learn about how, an Intel CPU works, and then we write some code, in this case C++, that exerts control over those features on the CPU. If you haven't worked a lot with CPUs, you can really boil it down into two major categories of information. So there's things, registers. So you've probably heard of the ones, EAX, EBX, things like that, the general purpose ones. But there's also a lot of registers in an architecture that exert control over a processor. So things like enabling features on the processor, like paging and virtual memory. There's all sorts of registers. It also describes the instructions, on the other hand, so the bits and pieces that drive the execution of those registers and move data in and out. So that's all fine and good when you're reading these manuals until you kind of realize when you open these up for the first time, it's a bit overwhelming. You kind of see that, man, this thing is over 6,000 pages in length. This is ridiculous. I'm going to spend, the next 10 years of my life just trying to understand this thing. Oh, and by the way, this is only the first, volume. There's actually 4 volumes of these things you have to download to get all of the information about the architecture. So great. It's kind of a long and a lengthy process to do this. So, the cool thing about, microarchitectures is there's more than one of them. So, one day somebody had the idea, hey, why don't we try and do virtual machines on ARM today? And so what do you think happens when you try to expand to more architectures? Well, you get another reference manual that's also 6,000 pages in length. And you get to read that and spend another 10 years of your life trying to understand what the heck's going on. So yeah, it's this constant cycle of just, ingesting so much information as a developer. So anyways, one day the task to try and add ARM support to Bearflank landed on somebody's shoulders. I'm sure you can guess who that is. Yeah, that was me. So before I was kind of dreading opening up a new manual. I'd already learned so much about Intel. But so luckily I was up one night reading just some random blog posts, and this caught my attention. So there's a researcher, his name is Alistair Reed. He does a blog. So he's a researcher who works with ARM, although I think he actually moved to Google recently. But anyways, he was a researcher at ARM for a very long time. I was reading through his blog, and this caught my attention. This is the, I'll just read it to you real quick. So it's ARM releases machine-readable architecture specification. So yeah, I'm kind of thinking, wait, machine-readable, like I don't have to read it? It's kind of piqued my interest a little bit. So yeah, I decided to kind of download it and take a look and see what I found. So here's what I found. So this machine readable manual, what it really consists of, it's 3 sets of downloads, and inside of those, there's a few different parts. So first of all, there's some XML files, and the XML files, they basically take the English language that describes how a processor would work, and it adds some better structure to those pros. So imagine you have like a keyword, the name of a register. Well, now it's got a convenient XML tag wrapped around it so that you can write, a script, go look for this tag. Oh, now you know this is the name of the register. So it's got a lot of structure kind of surrounding it. The other part of the manual is this thing called ASL. It stands for the Architecture Specification Language. So this is actually a new language that was invented by ARM specifically for the purpose of describing the semantics or the behaviors of what should happen on a CPU, given an instruction or a register that you use. That's what it's trying to describe. If you've worked with ARM before, you may have seen references to the term ARM pseudocode before. It's my belief that ASL really is ARM pseudocode. It's been evolving over time and getting better and better at describing how a processor works until now we're close to like a formal specification language that describes how a processor works. So if you see that, that's kind of like ARM pseudocode. The main thing about this, though, the main thing to take away is that this spec is easy to read by both a human and a computer. So you have this sort of bridging of the gap between, the problem of me reading the PDF and then converting it into code. It's kind of closing that gap a little bit. So this was first released in 2017. It's kind of a relatively new concept. But yeah, so to give you an example, if you crack open the ARM architecture reference manual, this is what you would usually see as a human. So things like registers are described in terms of tables. It'll have like a nice diagram that says, here's the size of the register. Here's some of the bits. They all have names within the register and, their positions within that register. So this is what you might see. In the machine readable XML version, you'd see something like this. So it's the same information. It's just that it's in a more structured way that's more easy for a program to go through and read it. In fact, this information, I believe now, is actually generated from this specification. So you can take the more machine-friendly version and link it directly to the more human-readable version. So you can see things in this slide like there's a tag called reg short name, and inside there is a SPSR EL2. So this describes the saved program status register for EL2 execution on ARM. And that's kind of what they look like. They also have things, all the fields. They've got things including like which privilege levels are you allowed to look at a register and under what circumstances does it behave normally. So things like that are also included in the spec. So anyways, after looking at these, I really got to wondering, I thought these might be useful for myself as a hypervisor developer. So we've got this whole layer in the Bearflank project called the Bearflank intrinsics. What that is, we have a function for every register and every field, every bit, everything that's named in the manual. We create a C++ function just for looking at it and setting it to a particular value. So I thought, I wonder if I can use this tool to just generate this whole layer, Bearflank, and be done with it. Then I can get on to the more interesting things. And so as it turns out, that actually does work really well. So this resulted in sort of a little spin-off project on the Bearflank ecosystem, something called Shoulder for ARM. I'll let you realize the way to connect your software to your arm is through your shoulder. So terrible name, I know, but that's what we called it. So naturally, I got really excited about this. I didn't have to write hundreds of thousands of lines of code, so I wanted to see what else could you do with these manuals. So I read some more of Alistair's blog, looked around for some more information. I stumbled across this quote that I thought was interesting, and I'll just read it to you. So he said, "But the specification can be used for much, much more. So download it and go do something surprising with it." And so I saw this immediately, being excited. Yes, challenge accepted. Let's do something cool with this spec. So first, I came up with a list of questions, things that I thought might be interesting to do with the spec. So here's some things that I thought about at a first glance. So I wondered if it was possible to generate a CPU emulator. So if you've ever used something like QEMU, is there enough information in these manuals to just generate an emulator for a CPU? I wonder if that's possible. So also, the manuals, they contain information about things like the name of an assembler mnemonic. If you're writing assembly code, what's the name that you're supposed to use for accessing a register or executing an instruction? That stuff's in the manual. It also contains the encoding for an instruction. So given this assembler mnemonic is seen, what like binary output should be generated to actually make that instruction. So can you make an assembler or a disassembler out of this information? And last, I had this thought that the spec, as all specifications are, they're abstract in nature. They aren't concrete. But CPUs are concrete. There's many instances of embedded devices. So I wondered if you could look at the abstract specification, compare it to a real physical CPU, and see if you could see any differences between the two. So it turns out there's people who've been thinking about this already as well. Those first two items, actually, there's people already actively working on this. So there's a really great group out of Cambridge University called the REMS project. There's a whole bunch of researchers working on this. They've got this whole language that they've invented called SAIL, and a spin-off of this called SAIL-ARM, in which they're trying to do exactly this, generating CPU emulators based off of a specification for ARM. And so this is a really cool tool. I've downloaded it and played with it. It's really powerful, actually. There's also a student, I believe, of there. It's just one guy. He's got another tool called HSARM, and this is working on deriving assemblers and disassemblers using this spec. So somebody's been working onto that as well. But that last item on there, I hadn't seen anything out there existing. So how could you compare the CPUs against the spec? So I thought I might take that on myself. Let's find out what happens when you try to compare them. So why would you want to bother doing that anyways? Well, I read this interesting article one time. It was called Big. Little Problems, A Tale of Big. Little Gone Wrong. If you're not familiar, ARM has a feature called Big. Little. It's when you take a really high performance processor and you put it right next to a really power efficient processor, and software can migrate between the two to either save power or run, more faster, I guess. So these guys found an issue. I think somebody was working on a compiler for Golang, the language, and they found they're just having crashes all the time for random reasons they couldn't point out. They found out that somebody on a Samsung Galaxy phone, they actually chose to implement their Big. Little with two different versions of the ARM architecture on the Big and the Little processor. So some things like instructions were just missing on one of the processors, even though they were supposed to be the same. So if you have a way to verify that your processors work how you expect them to, that's kind of important. The other thing is that, so closed source designs, CPUs really are, well, most of them are kind of closed source in nature. It's really difficult to verify how those CPUs work. So there's another really cool tool on the Intel platform by Christopher Domas. It's called the Sand Sifter. So this thing basically goes through and makes all sorts of crazy permutations of instructions on the Intel platform, and it helps you uncover hidden instructions that aren't disclosed by the manufacturer. So the thing about this, though, if you download this tool and go run it, it can take up to days to actually generate all of its results. So it's really difficult to go and actually verify how a CPU works when it's closed source. And the other thing to note is that if you've worked with ARM before, you might know that design by necessity doesn't quite equal an implementation. ARM purposefully leaves gaps in their architecture that they would like people who implement those architectures to go fill in details for themselves. So you kind of have this process where ARM designs a CPU, they hand off that design to another company who adds their own extra design to this, they go and implement that CPU, they make a real product. So there's this chain that happens. And it kind of seems like, if there's any sort of chain of events, there's room for error, especially if there's many humans involved along that chain of points. So that's why I thought it might be interesting. So with all this background in mind, I'd like to introduce you the tool that I kind of wrote to address this. So Scapula is the name for the tool. Once again, with the terrible puns, what goes inside of the shoulder? That's right, the scapula, your bone. So Scapula, it's open source. It's up on GitHub right now. It's under my company's group, AInfosec/Scapula is where you can find it. So what does it do? So Scapula, it allows you to do a couple things. First, it allows you, well, it reads the manuals for you, so you get that part for free already, and then it lets you create a list of assumptions about how you think the CPU should work. And then you can take your assumptions, turn them into executable code, and then go run them to check if those assumptions actually hold on a real CPU. So you can think of this a little bit like fuzzing on a CPU, where the lots of inputs that you're running into the CPU are the instructions. And then as you run all these instructions on the CPU, you can observe to see if any side effects happen that are either interesting, maybe a crash happens or something like that, or a crash doesn't happen and you were expecting one to happen. So it's, yeah, like fuzzing a CPU. So right now the tool, it's really focused on testing behaviors of the system registers on ARM. On ARM, system registers really are everything that kind of controls how the processor is set up to work. So there's also the instructions part of the manual. ARM has kind of purposely left out a lot of that information right now. I'll kind of get to that point a little bit later. But yeah, so for right now, this is what Scapula does. The tool is broken up into 3 different major components. So there's the main Scapula portion of the tool. This is a Python package for anybody who likes Python. I sure do. It's a Python package that reads the manuals for you. You get that for free. That's the part that lets you sort of generate your assumptions and generate basically C code that you can go compile and run on an ARM CPU. I also wrote a really small, lightweight operating system to facilitate execution of your test cases. So maybe operating system, it's not like what you'd think of in a traditional sense of an operating system. You know, it runs many processes at the same time. This is kind of opposite goals to that. I'll get to some more details about how that works in a minute. And the project also comes with a little minimal bootloader, so it helps with convenience of just packaging everything up into one little binary blob that you can deploy to your little dev board. So yeah, that's the 3 major components. I'll go through how each of them work in a little bit more details and walk you through some examples. So first, the Python part of Scapula. So your job in this framework is to write the Python code that generates some test cases. So I'll show you kind of line by line or little section by section how this works. So all you do to plug into this framework is you just declare a Python class that extends the Scapula generator class, and that plugs you in. That's about it. And then you kind of get 2 functions within your generator to pick and choose things that you'd like to do. So first, you get this little setup function here. And you can, in here, you apply filters and transforms so you can massage all the data in the manuals. There's like an overwhelming amount. So you can filter it down into something that's of interest to you, that you'd be interested in doing test cases about. So in this example here, if you look at line 4, we're using a filter to include all of the registers that belong to the AArch64 or 64-bit execution state. So it'll ignore all the 32-bit state. And it's also got memory mapped registers, so ignore those as well. The last part that you'll do, Scapula comes with a little writer utility that helps you write bits and pieces of C code that will eventually constitute a test case. So if you look at this line by line, line 8, if you can see that, you can check if a register is writable or readable. And then you can do things like declare variables on line 9. This will put a C variable in your program. And then you can do things like read and write the register, line 10 up here. And you can also do things like print information that you're interested in out to a serial port. So at the end of the day, when you run a generator, it dumps out and helps you generate some C code that looks like this. So this would be one example generated from the generator I showed you just shown previously. So keep in mind that it will generate one of these test cases for every register that you're interested in. So this is just one example of, one that was included in the set you were interested in. So great, we've got some test cases generated. The next thing is we need an environment to run those test cases. So this is where the Scapula OS component comes in. So normally an operating system, it's really focused on segregating and isolating different pieces of a processor so that it can facilitate lots of things running at the same time on that processor. So if you imagine Windows, lots of apps are running all the time. And that's the job of Windows, is to make sure that the apps kind of stay in their own containers. They don't harm the rest of the system. So Scapula OS has the exact opposite goal of this. It tries to break down as many privilege boundaries as possible so that you can have one thread of execution, if you will, that can span all of the security states on the processor. So I'll kind of walk you through how this would work using some examples. So if you're unfamiliar with the ARM architecture, privilege comes in layers that are called exception levels. Let's draw some parallels. So EL3 is the most privileged. It's called like the system monitor mode. Then there's an EL2 level is where hypervisors would usually run. There's another level called EL1. That's usually where an operating system would run. And then finally EL0, that's where an application would sort of run. So this is parallel to, if you're familiar with Intel more, it's ring 3, ring 0, ring -1, ring -2 from the top to the bottom. So the first thing you can do with Scapula OS is when it loads, it'll load you into the highest privilege level that is available to the software when it is loaded, and will take control of all of the levels where you're at and below. So you can do things like read, well, which exception level am I at right now? So that's the first thing you can do. The next thing you can do is you can switch to any other exception level at any other time. So imagine if you had an application that was running and it had a function that you could call, and it says, make me the operating system is the name of your function. And when that function returns, your application now is the operating system on that environment. So you can use it to switch back and forth between, whichever privilege level that you want, and it does it just by calling a function. So after you switch exception levels, you can see the privilege has changed to EL1 is the example we're doing here. So Scapula OS also comes with accessor functions for everything that you are interested in while you generated test cases. So for example, let's say we're interested in looking at the hypervisor control register for EL2. So you'll have the HCR EL2 is what its name is. It comes with an accessor for that. So the interesting thing though is that if you take all these 3 lines together, we were in EL1 and then we tried to access a resource that belonged to a more privileged level, EL2. So instead of crashing and having a fault happen, execution just continues seamlessly right through that sort of boundary, and Scapula will just launch your test case right back to where it was before. So if we back up a little bit, we're here before. Oh, my clicker is running a little slow. So if you're in EL1, you run this function to look at a more privileged resource. You can see the privilege changes to EL2 and your execution continues seamlessly to the next line. Another cool thing about Scapula OS, you can look at things such as registers or instructions that aren't even yet supported by your compiler toolchain. So the reason for this is, like I said earlier, there's enough information in these manuals to actually derive the encoding of an instruction that you'd like to run. So if your compiler toolchain, let's say you're using an open source toolchain, the GCC toolchain, and it doesn't quite support the latest and greatest features that are defined by ARM, they're defined in the spec. So the tool comes with a way to actually go use those before they're actually implemented by your compiler toolchain. There's some other cool things you can do. It comes with like a libc, so your test cases can do malloc and free. They can printf. Most of a libc is present there. It's backed by a cool project called Embedded Artistry libc. If you haven't seen that one, go check it out. Pretty cool. Finally, the last component that comes with the toolkit, it's like a bootloader that it's trying to make it convenient for you to deploy your test cases to a CPU. So it bundles up all the test cases you generated in Scapula OS, and it puts them into a single binary image that you can just go deploy and run. So right now, it's integrated with U-boot and ext Linux to facilitate just the couple of boards that we support right now, officially. So right now, I've been testing on the NVIDIA Jetson TX1 and TX2 developer kits. And I've also got these integrated with the Sail project that I was talking about earlier. You can run tests on this emulator that was derived from the spec. So I thought that might be interesting. You can run tests on the supposedly perfect gold standard that's derived from the spec. So all 3 of those are supported. All right, so now I've told you about the tool. You guys want to see how it works? Maybe thought we could do a few demos. So I brought with me today an NVIDIA Jetson TX1 developer kit I've got up here on the stage with me. So if you're unfamiliar, this is like a developer kit for a product from NVIDIA called the Tegra X1 processor. It's a Cortex-A57 processor that implements the ARM v8-A profile. So these are the high performance processors, the ones that not microcontrollers, they're for like heavy computing loads. So this was released around 2015, this development kit. I've seen these CPUs are currently used in things like the Nintendo Switch. It's a video game console. I've also seen them, they were part of the Google Pixel C. It's like a tablet that was released around that same time. And also the NVIDIA Shield Android TV also uses this processor. So it's in a few sort of consumer electronic devices right now. So before I run the test cases, I thought I might describe the questions that I'd be interested in kind of showing today and describe what should we be looking for. So let me describe what the demo will do, and then I'll show you. So first thing I noticed in the manual, there's you can see there's an XML tag for ARM defined word and then a res0. So what that means is there's a place in the architecture that a bit is reserved to the value of 0. In other words, you shouldn't really use it, just reserve its use. So I thought, what happens if you go to actually just read the reserved 0 bits? Let's just run that test and see what happens. You might think that they just give you 0. So let's see if that assumption holds. The next one, I noticed that a lot of the reserved 0 bits, they have this XML tag for field values or things that should be able to be written to there, and it's just empty in the spec. So I had another thought, well, I mean, maybe let's find out if we can reliably toggle any reserved 0 bits on and off. If it's not defined what the value is, can you find ones that actually work as if they are control bits? So yeah, let's do that one as well. The other interesting part, I found a few of these things in the spec. There's this key word in the ARM architecture called implementation defined. Usually these are spaces where it's up to somebody to take an ARM design and add their own sort of extra-ness to the ARM processor. So I saw this interesting register, actually. It's got a funny name, S1 underscore OP1 underscore CN underscore, etc. What it says, the description of this, though, is it's actually a register that lets you add implementation-defined maintenance instructions for the processor. So that's pretty cool. So why don't we go run and see what we can derive information around these and see if we can uncover anything, these extra instructions that aren't really in there. So likewise, with the instructions, there's another register that's defined like this, implementation-defined registers. So ARM also adds a spot for you to add your own registers to the architecture that can do whatever you want. So let's find if we can read and write and see if any of these things actually exist on a real CPU. So with that in mind, let's head over to my dev board. Give me 1 second and see if I can get this all hooked up. All right. Zoom in a little. Hopefully that's a little bit more visible to everybody. Okay. So I've got the test cases that I just described, I've got them preloaded on my dev board. So let's select the first one here. So again, let's read the reserved 0 bits and print out a message when they're not equal to 0. So let's see what happens here. So here it starts up, gives you a message, and we can see some results. So scroll a little. So yeah, as we can see, there's quite a few places where the manual marked some things as reserved 0, but they didn't actually give the value of 0 back. So if you're a veteran of the ARM architecture, I will tell you this isn't actually that interesting of a result, and this is one of those things that actually told my assumptions about the CPU were wrong, even though the manual is right. So it turns out there's some really detailed sections in the manual that say if you read a reserved 0 bit, it's actually, who knows what happens when you go read it. I don't know if it will be a 0 or 1. That's actually the defined behavior. So this one was kind of interesting. It changed my assumptions about what was supposed to be happening on a CPU. So let's reboot the board and look at some more test cases. Oops. Oops. All right. So the second one up here, let's see what happens if we can toggle any reserved bits on and off reliably and see what happens and print out if we find one. All right, so we get a whole bunch of results on this one. So I will disclaimer, my tools aren't exactly perfect yet. Some of these are false positives. There are some scenarios in which bits on the ARM architecture are conditionally reserved 0, and my tools aren't quite yet sophisticated to get all of those sort of edge cases. But what I will tell you, I'll direct your attention, if we scroll all the way to the top here, there's this interesting one that I saw at the top here. So if you can see this up here, there's this register called SCTLR_EL1, and we can see that bits number 30 and 13 were reliably toggleable. So it turns out that this register is called the System Control Register for EL1 on ARM. If you're from an Intel background, this is roughly equivalent to CR0, or the control register number 0 on Intel. It has a whole bunch of bits that are used for turning features on and off within the CPU. So as it turns out, I looked up those bits to see what they kind of were, if they had any references, if I could find anything online. And it turns out that in a more recent version of the ARM architecture, I believe 8.3, or it may have been 8.4, it was something pretty recent. It introduced these bits for the first time as enable bits for a feature called pointer authentication on ARM. So it's a really cool feature where you can basically sign your pointers, and then you have to use some special instructions that go and actually validate that those pointers haven't changed before it either executes them or loads them from memory. A pretty cool feature. So the thing is that this feature was first released by ARM in 2016. You can even find a blog post on ARM's official website that says, great, we're releasing the new version of the architecture. Pointer authentication is one of our newest and latest and greatest features. The thing is that my NVIDIA Jetson TX1, to the best of my knowledge, was released in 2015, a year prior. So this kind of leads me to believe that ARM might have some ideas kind of in the works, and they're sort of leaking their new features into a CPU's design potentially. So that's kind of one conclusion that I might draw from this. So yeah, kind of an interesting result. All right, so let's run some more tests. All right, so next one. Let's look at test number 3, which, I think I ran the wrong one. Let me reboot that real quick. All right, so the third test, this one's going to go out and it's going to search and see if there's any of those implementation defined spaces that offer instructions. Let's see if we can run any of those and they don't cause a fault to happen on the CPU. In other words, can you execute the instruction and it worked? So let's see what happens. So cool, let me highlight the output we might be interested in. So it turns out that there is actually, in fact, this instruction. So the output is for just one instruction. It tries to use it in a read and a write mode using 0 and Fs. So what does this say? So basically, there's an extra instruction that NVIDIA has chosen to implement and put into this Tegra X1 processor, and we can see that it works. I don't know quite what it does yet, but we've at least uncovered its existence, and we can see that it's there. So similar to this one, let's go see what happens if we look for some registers that NVIDIA may have added to this. All right, so let's look for implementation defined registers. So yeah, as it turns out, there's a whole lot of output that comes out of this test. So if we scroll all the way back up, I counted these up. It turns out that there's actually 17 registers that my tool has kind of uncovered, and you can see that they exist. And they have a variety of different sort of uses that it seems like. So if we look at this first one up here, the tool prints out if there's any bits that act as reserved 0 or act as reserved 1. We can see in this register here, it's kind of random, like some of the lower 32 bits have just random things that might be reserved 0 or reserved 1. If we look at this register here, we can see that the lower 32 bits, or the least significant 32 bits, are readable and writable, but the upper 32 are not. Those were reserved 0. So this might be a 32-bit value that you can read or write to this register. So yeah, a whole variety of different ones that all behave sort of differently. And yeah, we can see that they're there. I don't know exactly what any of these do yet, but I think that it at least provides a starting point for, if you want any reverse engineers in the room, maybe go look for references to these registers in any software or anything like that. So yeah. All right, let me switch back to my presentation now. Maybe. Oh. We've gone back in time a little. Okay, so again, to summarize some of these results. So So looking for toggleable reserved 0 bits, that turns out to be useful to help discover the potential for hidden features within the architecture. So we gave the example of pointer authentication. The feature may be leaking into designs of ARM CPUs before the feature is even announced. So that's kind of useful. But the other more important and useful to me, so I'm somebody who writes hypervisor technology. One of my primary jobs as somebody who's interested in writing a hypervisor is to provide isolation between many instances of operating systems that are sharing execution on a CPU. If you have reserved bits that aren't defined that are reliably toggleable back and forth, that kind of opens up the basis for a storage channel potentially to exist. You can put information in those bits, and the hypervisor may not know that they're even there. If they really are very reliable, that might even open up potential for a communications channel to exist. So if you can store information in a bit, the hypervisor doesn't know about it, then there's a potential that that information might leak into another virtual machine running on the same system. So those are important to me. I need to know where all these storage places exist within a CPU. So the other, interesting result, we can see that NVIDIA, in fact, has added their own secret sauce to the Tegra X1. So maybe this is documented somewhere I haven't seen quite yet, but we at least know that it exists. So something interesting you can do with this, if you know exactly how a particular CPU works, you might be able to actually fingerprint that CPU using a tool like this. So in other words, can you write a program that goes out and does these same types of tests on many different CPUs and then sort of figure out where it's launched? There would probably be differences. Let's say NVIDIA, maybe they have an emulator for the Tegra X1. Well, maybe it doesn't work quite the same way as the real hardware. You might be able to uncover, sort of detect which of the environments you're actually running in using techniques like this. Some other interesting results I noticed, I ran these tests on the Tegra X1, and it also has a spiritual successor called the Tegra X2. So the Tegra X1, it's kind of deprecated at this point. NVIDIA is not really using or marketing or, it's kind of just old news at this point. But the Tegra X2, I got my hands on one of those, the newer version. So even the same processor that's just one generation later had some slight differences between it. I wrote some tests that just go out and try to read all the values from all the implementation defined space on the processors. And it turns out there were in fact some differences. In fact, I found out that there's a register on ARM where you're supposed to just, advertise which version of, your processor are you implementing right now. And so, yeah, they have different values between the two processors. I didn't even know that register existed. So it's pretty cool. So to go over some of the technical challenges with the tool and some future room for improvement, I think there's a lot of ways that you could kind of go with tools like this. This tool is really new. It's just getting started. I think there's a lot of room for improvement. I hope that by making it open source that, you guys will be more clever and smart than me. You'll be able to find some more use cases as well. So, the first thing that would be really cool is if you could use the tool to switch between security states on ARM that are known as secure world and non-secure world. So ARM has a privilege model, not just in terms of exception levels, but it also has a sort of sideways privilege model called the security state. So I'd love to add the ability to just switch back and forth just as easily between the two security states. So you could test, how does one operation work in secure world versus non-secure world. The other thing, so ARM v8 processors, they come with additionally, backwards compatibility with 32-bit ARM execution. So this is called AArch32 state using the A32 instruction set. So my tool doesn't support execution on that yet, but it's something that's kind of in the works right now that we're working towards. So I'd love, by making this open source, if you guys could take this and port this to work on many platforms. I tried to make it as easy as possible. The process for porting this tool is you just need to define the address and memory that your bootloader will be loaded at and the address of a serial port. And that should be the only dependencies as of right now for porting this to a new platform. So hopefully it becomes easy for the community to try this out on a bunch more platforms. And yeah, so I also have some future hopes for this specification from ARM, so the spec itself. So as I mentioned, there's this whole language that they have called ASL, the architecture specification language. Right now, there really aren't any tools for interpreting that language or, discerning what it means. You can glance at it at a human and you can tell it's sort of a C-like language and you can sort of tell what's going on, but there isn't really a formal definition yet of that language. So it'd be really great if ARM had some kind of more tools for reading what this language is supposed to be telling us precisely. The other thing is that it turns out that ARM only open sourced to the public about half of this specification, and they've got a separate internal version of it that actually has ASL for semantics of instructions. So those don't exist at all right now. There's a lot of information about system registers and how they work, but ARM's kind of sitting on right now this other version that has extra information about instructions. So I really hope that they're soon going to be able to release publicly the whole architecture so we can do some more testing with instructions as well. I've also seen references to research papers written. Apparently, they have the same type of a spec for the microcontroller or -M profile on ARM, but that's currently not publicly available either. Right now, it's just for the ARM v8-A profile. It's versions 8.1 through 8.5. So those are up to date, but I really hope that they release other specs for the microcontroller versions of ARM as well, or the -R, the real-time profile as well. And last, I really hope that tools like these, I think they're so cool. I really hope that this kind of puts some pressure on Intel and AMD to start thinking about, maybe redoing their documentation to be expressed similarly to the way that ARM is. I've just found these tools so useful that I hope Intel and AMD also see the utility behind a spec written in this way. So I hope they see that that's actually useful to lots of people. So in conclusion, yes, these XML ASL manuals, they're extremely useful to builders and breakers alike. So thank you, ARM. Really, these are awesome tools for developers like me. These are seriously awesome. So thanks for releasing them. The other conclusion is that, the software security, it really is kind of rooted at the end of the day in assumptions that your software is making about its execution environment or the hardware that it's running on. So it's my belief that we kind of need some more openly available tools that really let you go out and verify how the hardware works so that you can sort of build your trust from the foundation upwards. And the last thing, I hope that at least I've gotten the message across that an abstract design doesn't actually equal a concrete implementation in the hardware world. There's differences, and it's important to be able to at least know what those differences are. So with that, thank you very much for attending my presentation, and we'll have some questions.
Any questions from the audience? Thank you very much for that. I really appreciate that for you. So my question is about the Scalar OS. What is the special about it, and what are the platforms that you are going to release in the future?
The Scapula OS, could you repeat it one more time? What's special about it?
Special about the Scalar OS. Yeah.
So the thing that's special about the Scapula OS is that it makes it really convenient for a test case to switch back and forth between any sort of different mode within the processor. In other words, it tries to break down all of the security boundaries on the platform so that you can just go back and forth between all of them and observe basically interactions between the security levels, or just a convenient way to check behaviors within different security levels. So for example, some of ARM, some of the registers are only accessible from, say, EL3, and some of the registers are only accessible from EL2. So you have to be able to switch back and forth to actually go look at those in different ways. Does that answer your question? Or?
Yeah, thank you very much for that.
Okay, yeah.
Any other questions? In that case, we'll go to the Slido question we've got here.
Some real world. Okay, so yes, somebody picked up on this. So some examples in the real world. So perhaps I'll point you way back in time to one of the first things that was released. I think it was Joanna Ratowska, the blue pill, if you've heard of that. This is a class of sort of malware, you could think of it as, called a VMX rootkit. What it does is it goes and it is basically a driver that goes and turns on virtualization features that are supported by hardware. And once those features are on, you can sort of do things to, emulate what's going on the CPU from underneath the operating system as it's running. So basically, yeah, this gives you just a really flexible and convenient way to go change how the hardware platform is working while the operating system is currently running. So that's one example. And another example of using Linux or Windows as a control domain. So an example of that, if you're familiar with a lot of the open source hypervisors that exist today, like Zen or KVM, a lot of them are really tied to this idea that there's a special gold standard operating system. It's always Linux, and it's given the special title of control domain, or DOM0 in Zen world. The thing is, it's always Linux. But in the Bearflank ecosystem, what's kind of special about it is that you don't actually have to use Linux as your control domain at all. You can use Windows as the special sort of all-seeing operating system, where conceivably you could use something like FreeRTOS or an RTOS as your control domain. It's not tied to this sort of model that's present in a lot of the existing open source hypervisors. So I hope that answers this question.
Did any more questions come from the audience? Then I want to thank Jared Wright and ask for a big applause for him again.
Thank you.